Hi guys, welcome back to my channel. Today I want to talk about aromaticity. This is pretty yield on the organic chemistry part. And then I will give you some examples after we quickly go over the criteria for a compound to be aromatic. All right, so let's dive right into this. So the first criteria is the compound has to be cyclic, right? It has to have all the sides, right? You can't have something like that, right? Or something like that. These are not cyclic, okay? And then the second criteria is that the compound has to be planar, okay? And this go hand by hand with the criteria that it has to be sp2 hybridized, okay? So the chemical bond that forms due to the sp2 orbitals are the sigma bond, okay? And then the pi bond are formed due to the p orbital. And then when we talk about how many electrons we need to have to meet the fourth criteria is that these pi electrons, pi bond, p orbital electrons has to meet 4n plus 2. That's a Tucker's rule, right? And then the third criteria is all the electrons have to be delocalized throughout the molecule, right? The very famous example is the benzene ring, right? So you can see the resonance happens all the time, meaning that all the electrons can be delocalized. This molecule is fully conjugated, okay? Not one single side is missing the electron density. They're all shared equally, okay? All right, perfect. So that's the four criteria of being an aromatic compound. Let's just dive into the examples, okay? So first, let's do carbon, okay? And then we're going to jump to boron, and then nitrogen and boron combination, and then eventually oxygen and sulfur, okay? So this carbon. So when I see this carbon molecule, what do I see? I don't see this. What I see is this. Okay, this is my carbon that has a positive charge. Why? Because I only have 3 bonds, okay? And then the valence electron number of carbon is 4. 4 minus 3 bond, that's positive 1, okay? That's why my carbon here has positive 1 charge, okay? I have no extra electrons, okay? And then also we know that this is a cyclic molecule, and then it is fully conjugated, okay? So now, my only concern is, does it meet 4m plus 2? How many pi electrons do I have, right? So I'm going to draw the p orbitals for you, okay? So basically, this double bond, I'm going to get rid of it, okay? And then the electrons in the double bond is just the electrons in the p orbital, okay? P orbital, okay? P orbital doesn't have to have 2 electrons in there. Even it's just the shape looks like that, okay? Remember X, Y, Z, right? P orbitals, but we only can have, we can really have just 1 electron in there, which is the case for these 2 carbons, okay? For these 1 electron in their p orbital. Why that's the case for these 2 carbons? Because these 2 carbons, I already have 1, 2, 3. That's the 3 sp2. That's the 3 sp2 sigma bonds, right? So I share electrons with 1 hydrogen, two other carbons that I used up 4 of my electrons, and then the 4th valence electron of carbon is the 1 electron in the p orbital, okay? So same thing. This carbon, I have a 1 sp2, another sp2, the 3rd sp2, and then the 4th electron is in the p orbital. This p orbital never got hybridized with another s orbital, unlike the sp2 orbital, right? So I really want to show you, because some students don't remember. Okay, I should have 2s here, down here. 2p, 2s, okay? 1, 2s, right? 3 xyz, remember? And then carbon 4 valence electrons, okay? If it was nitrogen, then I have 1 more, but carbon here only 4. And then hybridization, sp2 means s orbital hybridized with p orbital. How many p orbitals do I hybridize? I use 2 2p orbitals. So these 2 2p orbitals and 1 s orbital, they form 3 sp2 orbitals. 1, 2, 3, okay? So the other one, this 2p orbital is the p orbital that's left, right? It's so lonely, right? It has 1 electrons in there, okay? Okay, I hope that reminds you basic organic chemistry, maybe the first week content of your OChem 1. All right. And then also, I can also draw this carbon's sp2 orbitals for you. 1, 2, 3, right? And then because it's sp2, so it has to have this p orbital, but it's empty. Why? Why is empty? Because if I were to have electron in there, then this wouldn't exist. I wouldn't have positive 1 charge, right? To have positive 1 charge, I gotta just have this empty p orbital, okay? So my total p orbital pi electrons are 1 and 2. So 2 pi electrons. Does that fit 4n plus 2? It does, right? 4n plus 2. When n equals 0, this 4n plus 2 equals 2. So this is aromatic. Okay, all right, let's move on to the second. I know I spent a bit longer on this, but I just want to remind you all the basics. Okay, so this molecule, we're going to speed up a little bit. So this molecule, when I see this, I see this, I see this, I see this, and I see this, right? That gives me negative charge of this carbon, right? Because I have a 4 valence electron minus 3 bonds plus 1 and 2, the lone pair. So 5 give me minus 1, right? So that's the negative charge where that is from, okay? And then once again, this carbon's sp2, 1, 2, 3, okay? So sp2, 1, 2, 3. So this has to be both in my p orbital, okay? And then let me cross out this double bond and draw the p orbital here. They each have 1 electrons. So how many pi electrons I have in this case? 4 pi electrons. Does that meet 4n plus 2? No, it doesn't, right? There's no way you can get 4, whatever n you plug in. So this is not aromatic. Okay, perfect. Let's move on to the third one. So the third one, right off the bat, it doesn't even meet this sp2 criteria because this is sp3, this carbon, right? So this is not aromatic. And then MCAT likes to do what? MCAT likes to give you a super large compound, and then this R can be super big, like 4 rings, like I can have a lot more, you know, whatever, you know, there it can be super busy, and then you're like, okay, you get all lost. You're like, oh my gosh, how am I gonna count how many pi electrons? Don't bother. There's sp3 here. Okay, this is a thing MCAT likes to do. So look for sp3 first if you see some complicated molecules on MCAT. If they, okay, all right, ask you to identify the aromaticity. Okay, so that's the carbon ones. Okay, now let's move on to boron. So boron is a really special molecule. It's an atom, very special atom, okay? Because boron, it's in a different group than carbon. So it has like 3 valence electrons, right? So you may think, okay, so 1, 2, 3 sp2. Perfect. There's no p orbital. It's not fully conjugated. The electrons cannot be fully delocalized. But I mean, boron is special because boron, even though let's forget about aromaticity for a second. I mean, even not being aromatic, if you can distribute the electron density, that's a good thing for the molecule. And then some atoms cannot do that, but boron just has the ability to come up with an empty p orbital so that the electrons can really resonate, okay? So the empty p orbital can really share the electrons from the other p orbitals as I draw here, okay, as I get rid of the double bond and draw my p orbital. And I have 1, 2, 3, 4, okay, 4 pi electrons, okay. So even though it is fully conjugated, okay, the electrons are fully delocalized, but because of this 4 pi electron, I can't say it's aromatic, right, because it doesn't meet 4n plus 2, okay. All right. So that's boron. Let's look at another boron, okay? So another boron, once again, I have a 1, 2, 3, 3 sp2, okay? And then these are all sp2, okay? So perfect. They're sp2. It's a cyclic. It's a fully conjugated. Okay, let me just count how many pi electrons I have. So get rid of this, get rid of this. Okay, 1, 2, 3, 4, 5, 6. Does that meet the Tucker's rule? Yeah, it does, right? 4n plus 2. When n equals 1, we got 6. Okay, so this is definitely an aromatic compound. Okay, and then all the compounds like to be aromatic if they can, right? Because that provides stability. Okay, all right, so now let's move on to nitrogen. Okay, all right, as you can see here, the first molecule we're going to do is pyridine, okay? Pyridine is a base that I really liked back in the days when I took OChem, and then I always use pyridine as my base. It's small, you know, there's no steric hindrance. I like to use it for the mechanism, for the synthesis, I mean, those, 20 points, yeah? You get super sweaty and nervous during the exam, remember these days? Okay, and if you haven't taken OChem, you're still studying for MCAT, good for you, kudos for you, you can definitely do it, okay? All right, so let's look at this. Okay, I think I am missing a double bond for this pyridine molecule. Okay, now we're good. Okay, so now let me get rid of those easy ones, okay? So let's just forget about this part. Let's just get rid of those double bonds and then draw my p orbitals for my carbons. And then I know I have a 1, 2, 3, 4, right? 4 electrons in these p orbitals, okay? And then nitrogen, when I see nitrogen, I see this as well, right? Lone pair. It's 3 bonds, a set of lone pair, that it's a neutral nitrogen. Nitrogen likes it, okay? Okay, all right. So this carbon here, it has this, and this sp2, right? sp2 here. So this double bond that I crossed out must be what? The p orbital, okay? Okay, so 1 here. Okay, so because this is p orbital, so this must also be the p orbital that nitrogen contributes 1 electron. So this forms this double bond, which is the double bond that I crossed out, right? Since I'm already drawing the p orbitals, okay? So if that's the case, then the sp2 sigma bonds of nitrogen will be this, and this, right? Or this is the lone pair. Imagine it's a bond that's accepting a positive proton. That's what base does, right? Grabbing a proton, okay? So before it grabs the proton, let's count how many pi electrons we have, okay? So I have a 1, 2, 3, 4, 5, 6, okay? 6 pi electrons. That really meets 4n plus 2. And then all the other criteria, okay? So this is aromatic, okay? Now let's satisfy pyridine. Let's grab the proton here, okay? So after I grab proton, it's exactly the same thing. I still have 6 pi electrons, right? The only difference is now this set of lone pair in the sp2 orbital is grabbed this proton, okay? So you see, before pyridine grabs a proton, after pyridine grabs a proton, it's always aromatic, right? So pyridine is amazing, okay? All right, it's an amazing base. It's stable, right? After grabbing the proton and before grabbing the proton, it's wonderful, okay? And then what about this perol, okay? So let's see. This perol also has a nitrogen, right? And then when I see nitrogen, I also see 2 lone pairs, okay? But the difference is, let's just deal with the carbons first, okay? So let me get rid of this, and then do this, getting rid of this, do this, do this, do this. Okay, how many pi electron? 1, 2, 3, 4 in there, okay? And then let me think about this tricky nitrogen. Okay, nitrogen connecting with carbon, another hydrogen. It has to be sp2, right? It has to be sp2, then my set of lone pair has to be in my p orbital, right? There are 5 valence electrons of my nitrogen, not 4, right? So this neutral nitrogen really have p2 electrons in the p orbital. So that gives me also 1, 2, 3, 4, 5, 6 pi electrons, okay? So good job. Perol is also aromatic. It's stable, okay? All the compounds, they want to be aromatic. If they can be aromatic, being fully conjugated is the second best, okay? All right. Let's see if a perol is a base, okay? So imagine if I grab a proton, this nitrogen grabs a proton, the lone pair grabs proton, and then that will give me my nitrogen a positive charge. And then I think it's not aromatic. Why? Because this nitrogen is really, it doesn't have double bond. It's really all for sp3 here, okay? So sp3, no, okay? So I don't think Perot can be as a good base as pyridine. I mean, it's far worse than pyridine, obviously, right? First, this guy doesn't have six sides of the cyclic structure, and then we know six hexo, whatever, hexo, I can't say that now, but that's more stable. And then secondly, you see how it cannot be aromatic after it grabs a proton, so it's not a good base. It can't act like a base as pyridine does, okay? My point is pyridine is wonderful. Okay, all right, so now let's combine boron and nitrogen, okay? This is okay. Are you feeling better? This is actually not too complicated. So easy. Let's just do the empty p orbitals for all the borons, okay? Okay, and then nitrogen, they have a 3. They all have 3 sp2 already, right? sp2. Boron is also sp2, sp2. Everything's sp2, sp2, right? Boron's sp2 is, I'll use green, the 1, 2, 3, right? 1, 2, 3, and 1, and 2, and 3. Okay, so let me fill in the nitrogen's p orbital, okay, to see how many pi electrons I have. So just like the example we did for Perot, there's a 2 electrons in the nitrogen's, oh no, that's boron, right? Two electrons in the nitrogen's p orbital. So that gives me how many? 1, 2, 3, 4, 5, 6. Okay, 6 pi electrons. Okay, this thing is aromatic. Yay. Okay, all right, now let's look at a complicated one. Okay, actually it's not, right? And now we get the idea, because let's summarize. Okay, so this pyridine, this nitrogen with the double bond, how many electrons did I put in the p orbital? I put just 1, right? Whereas the Perot, and then this last example that I did, they don't have double bond that's drawn to the nitrogen, only the 3 sp2 orbitals, right? So they have 2 electrons in their p orbital, because there are 5 valence electrons altogether. 3 are shared with 2 carbons and 1 hydrogen, and then the other 2 have to be 2 in the p orbital, right? So really the easy way out, when you see a nitrogen that has a double bond, just put 1 electron in the p orbital. When you have nitrogen that doesn't have a double bond, it's usually bonded to hydrogen, then just put 2 electrons in the p orbital, right? So once you summarize that, you can do this really easily, okay? All right, so how do you do that? Okay, I'm going to draw the p orbitals. Okay, let me get rid of the pi bond p orbitals. I mean, don't do that on your MCAT exam, okay? I mean, this is just a process for me to instruct you, and then you can do it quickly on your MCAT, just in your head. Okay, all right, so let's assign electrons, okay? So I'll use a different color, okay? So the first nitrogen here. So the first nitrogen here, it's with a double bond. So let me put 1, okay, and then it's a carbon is 1, carbon is 1, carbon is 1, and this is nitrogen also bonded to a double bond. So just 1, and then carbon 1, okay? And then this nitrogen has what? No double bond, right? So I'm going to put 2, okay? This carbon is 1, this nitrogen is 1, because it has a double bond here, okay? So how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? 10 pi electrons. This is aromatic. 4n plus 2, when n equals 2, this gives us 10, okay? And it's fully conjugated, it's cyclic, it's perfect, okay? And then does that molecule look familiar to you? It should, right? Because it really looks similar to some DNA bases, the A and then the G, right? They're the purines that have 2 rings instead of a pyrimidine that have 1 ring, okay? So this really looks like AG, okay? So now I'm going to tell you the bread and butter of this video, which is all the DNA or RNA bases And then all the aromatic amino acids, all the amino acids that have rings, except proline. Proline, that's a cyclic structure, but proline really have sp3 in its side chain, right? But phenylalanine, tryptophan, tyrosine, and histidine, okay, they are all aromatic. So on MCAT, don't second guess yourself. They are aromatic, okay? That might bump you 2 points. I don't know. 2 questions. All right. So not 2 points. 2 points is a lot on MCAT. All right. So now let's move on oxygen and this sulfur, okay? And then again, when I see oxygen and sulfur, mentally you have to know they have 2 sets of lone pairs, right? And then they are both in the same group, right? They have 6 valence electrons. So after sharing one, having this electron sharing with the other carbon, 1, 2, you have 2, 4 more. So 3, 4, 5, 6, okay? All right, so that's the configuration, okay? And then let's get rid of those annoying double bond and then draw my p orbitals, okay? See how many? Well, 1, 2, 3, 4, okay? And then for the oxygen, like I said, all the molecules wanna have a aromaticity, okay? So one set of lone pair will also be in the p orbital, okay? So in this case, this molecule is fully conjugated. Electrons are equally shared all over the place, right? And then when we count how many pi electrons we have, 1, 2, 3, 4, 5, 6, 6 pi electrons, okay? So this is aromatic, okay? And then this thiophanone thing is just exactly the same, right? Exactly the same as the furan, okay? 6 pi electrons, it's aromatic, okay? So that wraps up my discussion. I give you plenty of examples. I hope that's helpful. And then calm down, just remember the 4 criteria, and then also the specialty of boron of having this empty electron, empty p orbital where there's no electron in there, right? But it is fully conjugated, so it does meet one of the criteria, okay? And then just count your pi electron number to decide the aromaticity. All right, I hope that's helpful.